Again, I'm going to talk about mean value theorem real quick. I hope you've already gotten this. So here's what the mean value theorem says. First of all, something I want to point out to you is there's two things got to be true before you use either one of these. Either MBT, and I didn't abbreviate this one. This one is called the EVT, extreme value theorem. You must have a function that is continuous before you can find extreme value theorem or mean value theorem. Now, mean value theorem not only has to be continuous, it also has to be differentiable. So the mean value theorem basically says that if you have some function, and I want to tell you guys again, I got people that keep joining late. You need to be here before 8:23. You're coming tardy, and then I may be teaching and miss you. So show up early, don't show up late. Okay, so extreme value theorem says that you may have some kind of a graph. It doesn't even have to be on a graph, but we're going to call it a graph. And let's say we got, we'll make it a, I don't know, something a little crazy here. But anyway, this says, and I shouldn't have put an arrow here, you're going to have endpoints. And by the way, you can use points anywhere on here from endpoint to endpoint. But this point right here is going to be some x and f of x. I guess we'll call this x1 and f of x1. And this point up here would be another x and some f of x ordered pair. So what the extreme value theorem says, as long as this is continuous and differentiable, that the slope between the endpoints, in other words, f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1, the slope of the endpoints, that slope of that deal right there, will equal somewhere the derivative of some other x value. Now they put c here, this is an x value. So in other words, somewhere on this graph, you're guaranteed at least one place where the derivative equals the slope of the endpoints. So you're going to have to find the slope of the endpoints and the derivative and set those equal. So like maybe right here, this slope right here would be parallel to this slope. And let's say right there. So this one would have 2. But the mean value theorem guarantees there's at least one of these where they'll equal the endpoints. So that's what the mean value theorem says. So does anybody have any questions off of any of the homework problems from 5.1 that you would like me to go over? Any questions
Yes.
off of anything off 5.1? If you have one, you can privately chat me. You can unmute yourself if you had one of those you wanted to see. And again, I still got people coming late. You need to be here before 8:23. All right, we're going to do problem number 16.
Number 11.
So let me find that problem 16 here. Okay, so there's 16 right there. Now, this one does not have a little calculator by it, which means you should be able to do this without a calculator. So it says a marathoner ran 26.2 miles from New York City in 2 hours and 12 minutes. Like all the other runners, he started from a standing position. During the last 5 meters, his leg cramped and he fell down and had to roll across the finish line. Proved that at least twice the marathoner was at exactly 11 miles per hour. So what we need to know is 11 miles per hour is a rate. And from the good old days, distance equals rate times time. That means that rate will equal distance over time. Now in calculus, we might make that a triangle, which is delta, the Greek letter delta, which is the change in distance over the change in time. Okay, so what we need to do is figure out the average velocity, the average rate. So the average velocity is going to be how many miles he went and how many hours he went. Now, I would recommend changing all of this into hours. So I hope you know that 12 minutes is like 1 hour multiplied by 1 hour over 60 minutes, because this is a value of 1 right here. So this minute and this minute reduces. So 12 over 60 would be 1/5 of an hour, or you could write that as 0.2 hours. So you'd want to get everything in hours. So your average velocity is going to be the change in distance. Well, how far did the person go? They went 26.2 miles. Okay. And what was the time? The time was 2.2 hours. And again, I'm using this 0.2 over here from changing it from 12 minutes into hours. So if I take this that'd be 262 over 22 miles per hour. And let's divide both those by 2. So what is that? 131 divided by 11. So that'd be 1 and 10/11ths. So we would end up having that this person went 11 and 10/11ths miles per hour was their average rate. So during the race, what that tells me is that during the race, this person averaged 11.10 miles per hour. Now this says we want to know at least twice that this runner was at exactly 11 miles per hour. Well, what we know is that is the average. Right here is the average for the whole race, 11 and 10/11ths, which is probably about 11.9 something. So anyway, we know that he started from standing. So he started at 0, and then he was running, and he had to get up at least greater than that 11 and 10/11ths miles per hour as he was going along there. He hit that once going there, but then he fell down. So once he fell down, that means he slowed back down and went back down to 0 kind of and crawled. So if you think about this as being velocity, he started at 0, he went up, and somewhere up here is 11 miles per hour. He passed that, getting to his average. He would actually have gone faster than that, but he would have passed that 11 miles per hour. And then when he fell down, he would have slowed back down below that, which means he would have hit it twice. So what we would want to say is, because he started at 0, because he started from standing, there were 2 places by the MBT theorem, and I don't really have room to write that. So you'd probably want to say something along the lines, because he started standing, which means 0 miles per hour, and averaged 11 and 10/11ths miles per hour, he would hit 11 miles per hour twice by MBT. Does anybody else have anything he needs? Oh, wait a second, I got another one here. 1 or 2, because I'm getting 0 as a slope and it just doesn't seem right. Okay, well, you remember I told you, going back to this picture, that I told you this, oops, went too far. Let me get back the other way, sorry. I got crazy on hitting my symbols. This is the MBT theorem, what the MBT says. Well, Rolle's theorem says that if you have an endpoint that starts at 0 and it gets back to 0 again, that the slope where the y's are equal, the slope here of 0 is going to happen at least once somewhere on the graph. That's what that says. So when you're doing Rolle's theorem, you will always get 0 for the slope, and you're trying to find the x value that makes that true. So I will go and do problem number 1 and let you see that. So we've got to find, this is what we get out of here with 0 and 4. So we do f of 0, which gives us 0, and f of 4, which gives us 16 minus 16, which is 0. All right, so what that means is this graph at 0 is at 0, And out here at 16, this graph is at 0. So this graph is going, it is a parabola. Let's see. Oops, I put 16, that should be 4, sorry. At 0 and 4, this graph is 0, and it comes down and comes back up like this. So we want to find, again, you're going to have 0 minus 0 for the slope. This is the average rate of change, like it should put instead of m. You should start using algebra or calculus. The average rate of change is 0 over 0 minus 4 over 0, which is 0. And then the derivative. The derivative of this thing is going to be 2x minus 4. So we want to find where this derivative equals this slope. So 2x minus 4 equals 0 is going to be where x equals 2. So x equals 2 would be the x value where this slope would be 0. So in other words, right here at 2 would be where that is 0. So you are not making a mistake. Number 11, let's go look at it. Okay, so we're doing the same thing we had a minute ago. Now this one you got to be careful of, because remember, in order to use mean value theorem, your graph has to be continuous and differentiable. And because there's an x in the denominator, this is not continuous where x is 0. Well, 0 is not on my interval, so I'm okay, because when you plug a half in and every number between a half and 2, this thing is continuous there. So again, I'm going to find f of a half. So I'm going to get 2.5 divided by a half, which is 5 halves, is what 2.5 is, and multiplied by the reciprocal, and I get 5. So I got 1 point that's a half 5. And my other point is going to be 4 over 2, which is 2. So 1 point's a half 5, the other point is 2. So I'm going to get that 5 minus 2 is going to equal over 1/2 minus 2, which is going to be 3 over negative, let's see, what is that, negative 1.5? So it'd be negative 3 halves. Flip that upside down. I believe we get negative 2 for that, don't we? Because that'd be 3 over 1. You flip that upside down, the 3's will reduce. And this has to equal the derivative of this thing somewhere. So I need to find the derivative of this. So I would probably rewrite this without doing quotient rule. You can do quotient rule, but what I would do is I would take this thing and I would put x under each part individually and get 1 plus 2 over x, which would be 1 plus 2x to the negative 1. Now again, you could do quotient rule and it'll work out all beautiful, but this would be way faster to do a derivative of this. So I want to find where the derivative of the 1 is 0, do power rule here, and I'm going to get negative 2x to the negative 2. We're looking for where does that equal negative 2. So then we're going to change this down to the bottom. So then I'm going to multiply that over, and that's going to give me negative 2 equals negative 2x squared, and you divide by negative 2 and you get 1. So we're looking for where x is equal to positive or negative 1. Now if I wrote that down for my answer, I would be wrong, because I put down an answer that doesn't work. And the reason it doesn't work is because I have this interval. I'm only going from 1/2 to 2, so the negative number is not in that interval, so the only answer that works for this is x equals 1. Okay, so does anybody else have anything on that 5-1 homework? Okay, I'm going to go and do the notes for extreme value theorem now. So this first page is mainly reading and trying to understand what it's telling me. So this says extreme of a function. In calculus, much effort is devoted to determining the behavior of a function over an interval I. Now that interval is x values, the domain. We will investigate such as, does f have a maximum value over the interval? Does it have a minimum value? Where is the function increasing? Where is the function decreasing? Throughout this unit, you will use derivative to answer these questions and apply them to real life situations. A function does not have to have a maximum, does not have to have a maximum or a minimum on an interval. For instance, if you look at figure 1, okay, so it says you can see that there is a minimum value. You notice these endpoints are filled in, right? So these endpoints are included. This is a minimum value over the whole graph, and this is the maximum value over the whole graph. Now, if you look over here, there is a minimum here. This still has a minimum, but up here, do you notice this circle is open? So what that means is you can't get a maximum because I can always put another decimal, add another decimal to the place to get closer to this open circle and never reach there. There is not an exact value here. So because there's not an exact value here, this does not have a maximum. And then if you notice here, they put a hole down here at the bottom. And again, I can get closer and closer to this hole from both sides by adding decimals and never reach that point. So there's no minimum here, but if we fill this back in, there's a maximum here. So the extreme value theorem says if f, and this is big, you have to have that f is continuous on a closed interval. In other words, the endpoints must be included. The closed interval means the endpoints are included. The a and the b are actually in it. That's why they have brackets. And f is guaranteed, if you have this situation, if f is continuous and you have on a closed interval, the endpoints are there, then f is guaranteed to have both a maximum and a minimum. And then he put some pretty pictures down there that you can look at until it talks about them in the real world. Relative extrema. Now, here's the graph of this function, and it has a relative max at 0, 0, and a relative min at 2, 4. In other words, this graph keeps going, okay? That graph keeps going, and in this relative area, relative means in the immediate area around there, this is the maximum. Now, this is not the maximum of the entire graph because this graph keeps going up forever, and there are values over here that get bigger than this. So this is in this area, that is the maximum. And also over here, in this relative area, that's called a relative min because in this area, it's the smallest, even though over here, it gets lower than that. So relative max and mins happen when you don't have endpoints, when the graph keeps going. So to make it easier for you to think of, a relative max as being the peak of a mountain and a relative min the valley. So he's calling this the mountain. It looks more like a hill to me. Note that each relative extreme of the derivative is 0 or does not exist. So here's a big deal right here. This is a big deal. Critical numbers. Critical numbers, you must be able to find them. Critical numbers happen twice. It's where the derivative is 0 or the derivative does not exist. So those are your critical numbers, and we're going to have to find those. So I believe this says what I just highlighted there, right? Yes, where the derivative is 0 or where the function is not differentiable. In other words, the derivative does not exist. That's where your critical numbers are. So big deal that you get that because we're going to have to find critical numbers. It will be on your quiz and your test. Let f be a function whose second derivative exists on an open interval. Okay, so relative extreme. It says if there's an open interval containing c, which f of c is a maximum, then f of c is called the relative maximum. Okay, so this is, and okay, so the big thing here is open interval, meaning that there are no endpoints. And this is also open interval, meaning no endpoints. In other words, arrows, they go on forever. This is where the relative max and min occur. And then he also, sometimes they call it relative extrema. Sometimes they call it minima and maxima, but that just means relative max and minima. This means that's the plural. There could be more than one. That's all that's saying. We already talked about that. So here's an example where you have a maximum. See this maximum right there? That'd be the maximum of this, but you can't do a derivative there because there's a sharp turn. So this c value, that x value for that point, is a critical number because you can't do a derivative at a sharp turn. And then here is where a derivative is 0, which gives you a horizontal tangent line. That's also where max and mins occur. So this is where you find the critical numbers. Okay, so if f has relative max and min, c has to be a critical number. So that's why critical numbers are big. All right, so f is continuous Now notice these are also equal, so this is the same. This thing right here means the same as A to B. This thing right here and this thing mean the same. It means the endpoints are included because they have equal, and it's differentiable from A to B. Now this means this. Now the reason it does not include the endpoints on differentiability is you cannot do a derivative at an endpoint. So that's why these are not equal. So if you look, to use this theorem, you got to have continuous, including the endpoints, and differentiable, not including the endpoints. Which one of these could be false? All right, so this says a derivative would have to equal the slope of the endpoints for some C. Now that right there should look familiar. This has to be true because it says these two things, and this is mean value theorem. This is 5.1. Down here, F has a minimum value. Well, we're including endpoints, and we're saying it's continuous and differentiable from there, so that means that this has a maximum and a minimum. This is an EVT theorem, so this one has to be true. Likewise, this also has to be true because of EVT. So EVT says these two things must be true, and MVT says that must be true, so this is the one that does not have to be true. So to give you an example, let's say I just drew a line from here to here. See, this has a maximum here, and it has a minimum here, but there is no place where the derivative equals 0. There's no place this has a 0 value. There's no place the tangent is 0. The tangent would be this same slope as the line. So that's why this one is not necessarily true. Could be true, but not necessarily. Coming down here to this second problem, the function f is defined on a closed interval 0 to 1. So there's your 0 to 1 and satisfies this. So f of 0 equals f of a half equals f of 1. On an open interval from 0 to 1, f is continuous and strictly increasing. Remember another name for strictly increasing, that means increasing the entire time, is the word they have used on the AP test before is monotonic. That could be strictly increasing or strictly decreasing is monotonic. It could be either one of those, okay? So it's kind of important that you get that, remember that monotonic word because they have used that in the past. So anyway, this says, which of the following statements is true? All right, so f contains both a minimum and maximum value. F of 0, 1. Okay, so maybe we ought to draw a picture of this. So if I were drawing a picture of this, and this is 0, we'll call this 1, and we'll call this a half. It says that all three of these y values are the same. So wherever I put a y value at 0, there would have to be the same y value at a half, and there would have to be the same value at 1. Okay, so opening, so f contains both a minimum value and a maximum value over the interval. Okay, so let's see, f is continuous. Now it does not say differentiable. It says, wait a second, which one of the following statements is true? F attains both a minimum and a maximum. Okay, so now we could draw a picture of a continuous graph, not including, do you notice it says not including the endpoints, it's continuous. So in other words, what if I had a graph where this was open and this graph was doing something like this and then this was open? So this says that the open interval, meaning that this function is continuous, not including the endpoints. Do you see that? So this is a graph not including the endpoints that is continuous, but you do have a point here and here. Now it says 0 to 1, not including those, is continuous. So it says f has both a minimum and a maximum value. Well, this has no minimum because of open and no maximum value. so it's not this one. F attains a minimum value but not a maximum value. Well, again, this doesn't have a minimum or a max, so it doesn't have a minimum. F contains a maximum value and a minimum value on the closed interval. Well, again, neither one works. And this would be the one. It has neither a min nor a max. So there's no guarantee, and it's because these are not in brackets. If these were in brackets, then the first three, actually, where there's a max and a min, would be guaranteed by EVT. But because this was not in brackets, the endpoints do not have to be continuous. So that's a pretty tough problem. Let's see what's next. Okay, last problem. Let G be the function of this thing, where K is a constant. For what values of K does this have critical points? Okay, so what we got to do on this problem is find critical points. So I'm going to abbreviate critical points as CP. Remember, this is where the derivative is 0 or the derivative does not exist. There is none. You can't do a derivative. So we've talked about where derivatives can and can't exist. So what we need to do is we need to find the derivative of this function right here. We're going to find the derivative of this thing. So this is a product rule. And that reminds me, on the test, I told you guys not to do any typing, to write all of your work down on paper and then upload pictures. Some of you just gave me answers in the box and didn't listen. So you guys that are here probably did, but anyway, you probably did it okay because you're here. I can't see what that number is. That says e to the kx, I think. Yes, e to the kx. So it's first derivative of the second, and then we got to do the derivative of this exponent, which is going to be a k. So let me put a k. I'm going to move that k to the front because it's a coefficient. It's some constant. Okay, and then plus the second times derivative of the first. Okay, so there's my derivative. So then I'm going to set this derivative equal to 0 because this is where we want to find our critical points, where the derivative is 0 or does not exist. So I'm going to factor out my GCF. So if I factor out my GCF, let's see here real quick. Actually, there's a couple things we can do here. Because he gave us, it has a critical point at x equals 3/2. We could have found that. But let's go ahead and plug our 3/2 into this function. Because this right here tells me that g prime of 3/2 equals 0 because it's telling me there's a critical point here. So I'm supposed to plug in my 3/2. All right, so let's plug in 3/2 here. So I'm going to get k, and 3/2 squared would be 9/4. And this would be e to the 3/2 k plus 2 times 3/2 e to the 3/2 k equals 0. And again, we're trying to find k, right? So let's see what we got here. So these 2's will reduce. All right, so if you look, we have a common factor of e to the 3/2 k that I'm going to factor out. When I do, I'm going to be left with 9/4 k plus 3, because this 3 is still in there when I factor that out, equals 0. Okay, well, this is where something that's really important comes into play here. I'm going to come down here where you can see this, and that is this e to the 3/2 k. I hope you all remember from exponential functions that exponential functions go like this. In other words, there is no place where an exponential function hits the x-axis. So what that means, e to the 3/2 k never equals 0. So there's no answer, nothing for this part. You get no value for this, no solution for that part, because there's nowhere that graph will hit 0. And the other part we got to find is where 9-fourths k plus 3 equals 0. So that's going to be where 9-fourths k equals -3. And we'll multiply by the reciprocal. So these all reduce to k. And over here, this 3 and 9 will reduce to here, so we'll get -4/3. So the answer that we're looking for is when k equals -4/3, the derivative at 3/2 equals 0. So that's our k value. So that's the kind of stuff you're going to be doing on your worksheet 3.5.2. And extreme value theorem and critical points are the big deal. So does anybody have any questions about anything? Okay, so this video I'm going to put online is kind of a long one because we did some problems off of 5.1, but this is how you're going to be doing your homework on 5.1, 5.2. I'm planning on having a 5.1 quiz tomorrow. So tomorrow I'm going to ask if you got any questions left on 5.1, and if not, we're going to take that. You're going to take that quiz after class. I'm going to put it online. Okay? Anybody got any questions on anything? If you got questions, man, you got to ask them. All right, then I will see you guys tomorrow. Try to be here on time. Try not to be here late. Some of you came in way late. Please get here when you're supposed to so that we can get all this done. Have a great day, and I'll see you tomorrow. I hope you're all doing well.